In this, we are going to learn one of the applications of calculus to the to how to find the work done by a force. So the calculus is important, especially when the force is varying, because there are situations where the force changes. But if the force is constant, we really don't need calculus for that. We can just get the work easily by multiplying the force by the distance. But here the situation is the force is changing. So if the force is changing, we cannot do that. So we need calculus to get the solution for that. So let's talk about that. Before we do that, we're going to talk about a few things that are needed. So we're going to start with the force and the acceleration. So the force and acceleration. Force and acceleration. Force and acceleration. So let's say there's a mass sitting on a frictionless surface. So there's no friction. We assume that there are no other forces than the force mentioned here. And then what we can do is we can measure the distance. So let's say that's the center of mass. So the mass is m. So what we can do, we can start from a position and try to measure the distance. Let's say we measure the distance to the center. Uh, and let's call it this is the st. So the distance at time t. So we call st. It's a function. Now we know that according to the Newton's second law. So by Newton's second law, Newton's second law, we know that the resultant force is proportional to the acceleration. So it's A for that. A resultant force is proportional to the acceleration. And then when there's a proportion, what we can do is we can write this as an equality using a proportional constant. So the proportional constant becomes the mass. So this is the Newton's second law. So F equal ma formula. And what we can do is we can write them using a little bit more calculus here. So we can say F equal ma, that's the formula, Newton's second law. Now A is acceleration. Acceleration is, according to calculus, we know that's the second derivative of the displacement function. So that means we can write this one as m times the second derivative of s. So this is useful for us. So this is the first formula in this section, and if you are taking calculus, this will also be useful for that. Okay, yeah, not calculus. If you are taking physics, you need this. Good. And then there's a fact. Sometimes what happen, we need the acceleration due to gravity. We know that if there's an object, then the gravity for exert and force. That force generate an acceleration. Okay, and then we assume that that's roughly 9.8. So so I'm going to write this as a naught. So we can see the acceleration uh, due to gravity. Due to gravity, we normally write this as a g. The acceleration due to gravity is g. We know is small g, which is, we assume that roughly 9.8. So for calculations, we can use the number, and the unit is ms negative 2. Okay, so we can use we will use that also. That's like a constant. We assume that's a constant. It's not a constant because this is changing from, if you are closer to the equator, that's a one number, and if you are close to the pole, that's another number due to the rotation. Okay, but we assume that is 9.8 roughly. Okay, so those are the facts, and then let's also talk about some other units because there are two common units that we use for work problems. So let's talk about that. So I'm going to go with the SI units, the standard units. So the SI units, we are going to work with both. So the unit for mass is kilogram, the standard unit, kilograms. So we can write as small k and a g, a kilogram. And then we have displacement. Displacement, which is we measured using meters. So it is small m. And then we have force. Force. Force we measured by newtons. Newton is a scientist, so we can use a big N. So if it's the name of a scientist, it's a uppercase. If it is not, it's a lowercase. That's the rule. And then acceleration. Um, the standard unit is meters per second squared. So that means m is -2. And then we also use some another system, the US system. US system, which is difficult to work with due to some numbers, some ratios, because we know that in the SI units, it's easy to convert from meters to kilometers, centimeters, like that. It's always a power of 10, but that doesn't work in the US system. Okay, so but we need to know how to work with both systems. So for the force, we use pounds. Okay, pounds. The unit is libra. So libra. So we use lb. Okay, pounds. And then for the displacement, we use feet. So we say ft. Those are the common ones that we can use. And then when we do problems, I'm going to use both, so then you can learn how to apply the two. Okay, so as a first example, let's try to do like a simple problem just to see the connection between the acceleration and the displacement. So let's start with this problem. So let's do this problem. A force of 6 Newton is acting on a block of mass of 3 kilograms, which is placed on a smooth surface. The object is initially moving at a speed of 4 meters per second. 4 meters per second. So let's try to answer these questions. So the first one, find the acceleration. Find the acceleration. Okay, find the acceleration. B, find a formula for the distance traveled. Find a formula. Find a formula for the distance traveled. And the third one is very interesting. Find the distance traveled in the third second. Find the distance traveled in the third second. Find the distance. Find the distance traveled in the third second. Third second. So first second, second second, and third second. Good. So let's draw a situation. It's gonna help you to kind of absorb what's going on here. So there's object sitting on a smooth plane. So this object. So it's there's a force F. There's a constant force which is 4. So let's say you measure the distance at this point. Now this has gone st distance. So that's st. Starting from that. So the initial speed says that it is 4. So initial speed is 4. So that's the situation. So there's an object moving at 4, and all of a sudden you're going to start applying a force actually not 4, 6 Newton. So you can start applying a force of 6 Newton. So the question is, what is the acceleration of the object? And then find a formula for the distance, and then find the distance traveled in third second. So it's not a difficult problem. What we can do, we can start, because we need to find acceleration, we can use the first formula, the Newton's second law. So let's do it. So we can say by the Newton's second law, by Newton's second law, which is F equal ma. So you can see that 6 equal m mass is 3, a we don't know, and then this says that a equals 6 divided by 3 2. The unit is I can write the easy, but I'm gonna write all these steps. So which is 2. Let's put the unit in there. So it is m is -2. So that's the acceleration. That's the first part. And in the second part, they're asking find a formula. So to do that, we can start using we introduce more things. For example, we introduce the distance into the picture. So let's say if S is the distance traveled like whenever you start measuring. Okay, so yeah, I'm not going to mention that. That's what the distance travel. You start measuring at one moment, so and then you count the distance from that. So if S is the distance traveled from, you can say, from its initial position. Initial, when you say initial, it need not to be at rest. It can be some moving object. You exactly start measuring time from one point. Okay, so that's where it can still have some speed, initial speed. There's nothing wrong with that. From its initial position, so then we know that the acceleration is a second derivative. So we can write this one. The second derivative of the displacement is the acceleration. Okay, and which is equal to, that's what this is. Now what we can do, so we have this formula. We know that the second derivative equal to 2. That's the acceleration. So what we can do, we can integrate. So by integrating, so what can happen, this is second derivative. When you integrate the second derivative, it's going to be the first derivative, ds over dt. Ds over dt we normally call the velocity, so we say v. Let's put v. So v equal that. It is simply the integral of that, integral of 2. So that means it is 2t. What happened? You're going to introduce a constant. I'm going to call it c1. Now how to find this constant? So I'm going to do it here, but we know that there's an initial speed. Okay, we're going to use that. So at the time t equals 0, we know that the speed is 4. That's given. Speed is 4. So that means 4 has to be equal to 0 plus c1, and this says that c1 equal 4. Okay, so that means since c1 equal 4, now we can plug in there. Then we have this formula. So that means ds over dt is simply 2t plus 4. So that's what we get. Okay, so we go one step closer. Now what do you want to do? We still don't know s. So what do you do? We have to integrate it again. So let's do that. Integrating again. So what we have, we know that s, which is the integral of ds over dt, when we integrate the derivative, you get the function back. So we integrate. So what we have, integral of 2t plus 4 dt, that means t squared. It's not clear. What is this? That is t squared plus 4t plus c2. Now what we can do, we need to find the C2. So for that, we know that the initially at t equal 0, we know that c equals 0. So then we have 0 equals 0 plus 0 plus c2, which says that c2 equal 0. So therefore the st equal t squared plus 4t. This is a distance, so the unit is m. Okay, so the unit is m. Okay. So that's that. Now let's do the part C. So what the part C says, they're asking the distance traveled in the third second. So the distance traveled in the third second, What the third second means? So we can start from the beginning. This is the first second. And then this is the second, and 1 to 2, and the third second is this one. Okay, that means that time goes from t equal 2 to 3, t equal 2 to t equal 3. So that means the distance is simply integral going from 2 to 3. The distance, the velocity function, you integrate the velocity function from 2 to 3. So that means it is 2 to 3, 2t plus 4 dt. So you can see it's going to go through a similar argument. So this is t squared plus 4t, evaluate at 3 and 2. You don't need to add the constant here. It's a definite integral. So let's plug in 3. So it is 3 squared plus 12 minus 2 squared plus 2 squared plus 8. So you end up getting, what do you get? You get 12 minus 12 cancel 9. So 9 is the distance of the meters. So that's the distance traveled in the third second. Good. Now what we can do, we can discuss one of the important one in this section. We're going to derive formulas for the work done by a force. So let's derive the formula for the work done by the force. So work done by a force. So we need to consider two cases. The first case is type 1, which is the force is a constant. So the constant force. So if you have constant force, so what's going to happen? Let's try to draw the situation here. So we have a mass on a frictionless surface. So you can apply a force. So what's going to happen? The center of gravity moves. The center that move from that position to this position. So that's the force applied. It's a constant force. So this is the new position. So that move by d distance. Let's say this is d. This move by d distance, and then what the theory says that the work done by is defined as the product of F and D. So there's a F force, you're gonna pull D distance. So the work done is F times D. That's how we define. So the work is defined as the force times the distance. Force times the distance. Distance moving in the direction of the force. So that is the W equal FD. Okay, so that's the formula. This is when the force is a constant. So this is equation number 2. So let's talk about some units. So units. Uh, if uh, if the force is in Newton and the distance uh, in meters, the work is given by Newton meters. You can multiply the two, which is it's called Newton meters. Just write. I will write it like that. By Newton meters. Uh, by Newton meters. Newton meters. So we write this one as Nm. Oh, this Newton meters has one symbol called joule. Or by joule. Uh, so joule is a scientist, so we use the uppercase J for that. Joule. So we use joule. If the force is in Newton and the distance is in meters, the work is given by joule. Okay, that's a standard notation. And then the other one. So if F is in pound, if force is in pounds, that means libra like lb, and distance, d in feet. The work is given by foot pound. We normally write as FTLB. Okay, so those are the standard things that we use. Those are two things. First one is the SI unit. The second one is the customer unit in US. Okay, so we need to know how to solve problem in both. Okay, so now let's try to do a problem in that. So let's look at this problem. So find the work done in lifting a 1.4 kilogram book 0.6 meters off the ground. So the problem is clear. So there's a book which is 1.4 kilogram, and then you're going to lift it upward 0.6 meters. And what is the work done? And you can see that in this case the force is fixed. What is the force here? You have to apply a force which is equal to the weight but in opposite direction. Okay. And the second part, how much work is done in lifting a 8-pound weight 6 feet off the ground? So the difference between the two problems is one is given in kilogram, the other one is given in pound. So that's the difference between the two. And let's see how we do the two problems. So the first one, so let's draw it. So it's a book. So we have a book. Okay. So there's a book. So what we're gonna do? So the weight going down. So I'm gonna write W. That's the weight. So what we do is we can apply a force which is equal to W in size but in the opposite direction, and that's the force you need to lift the book. So we're gonna put the F force and you're gonna go up, and you can see the weight doesn't change. We assume that, and then it's a F fixed force and you go up 0.6 meters. So the rest of the calculation goes like this. So the force F is equal is equal in size, okay, to the weight, but in opposite direction. So that means F is simply given by mg. When it is given in kilogram, you multiply by the gravitational acceleration. So that means it is 1.4 is the weight. Actually, let's put the units there. So kilogram, and then g is 9.8 m/s -2, and then what we're gonna multiply the 2, so you're gonna get 13.72. So these are the standard units. That means force, you get the standard unit, that means Newton. Okay. So if they are in a kilogram and ms -2, the force in Newton. So that's the standard unit. Okay, now very easy. Then we can calculate the work done. So the work done is simply a W equal Ft. It's a constant, so we multiply by the distance. So the work is, we calculate, is 13.72 Newton, and then the distance, you have to write this in meters, so that means 0.6 meters. So if you're given in centimeters, you have to divide by 100 to convert into meters. So this is roughly 8.2 joule. Why joule? Because we use a standard unit for those two, that means your answer is coming from joule. Okay, good. Part B. In part B, what they're asking, so it says that the object is 8 pounds. So you don't want to convert in this case. So that's the difference. So you can say here, the weight is given. So that's the difference. Weight is given. So if the weight is given, you don't need that extra step by multiplying by g. So that's the major difference. Okay, so the work done so the work done is W equal Fd. So you're going to simply multiply the two. So it is, F is given in 8 pound, and the D is given in meters. It will be meters, and then you multiply the two, so you're going to get 48 foot-pound. Okay, so that's the work done. So your unit is foot-pound. So let's have a note here, because this is very useful. That's where we sometimes get stuck or make mistakes. In part B, we do not need to, we do not need to, or we do not multiply. We do not multiply by G, which is 9.8, since the weight is not the mass, it's a weight. Since the weight is given in pounds, okay, which is considered as a weight. So that's different. Okay, good. So this is a problem when the force is a constant. Next, what we can do a problem when the force is varying. So type 2 varying force, varying force. So this is the situation. So they say this object, there's an object sitting on a smooth surface. So now what we're gonna do is we're gonna use a force to move from A to the B position. But the thing is that in this time the force is changing. It's not a constant force, it's a changing force. So what we're gonna do, we're gonna divide the interval into n parts. So say x0, x1, x2, like that. This is xn. So you're gonna divide it into n many parts. So what we're gonna do, we're gonna calculate the work done in a very tiny small interval. Let's say you're gonna pick a interval xi minus 1 to xi. Pick an interval like that, And then what we're going to do, we're going to calculate how much work needed to move from x minus 1 to xi minus 1 to xi. Okay, so we're going to call this is delta x, the gap. So we're going to see how much work you need for that. And then you can see that you can make that that interval really small. So uh, because of that, you can assume that this force is a kind of constant. So what we do, let's pick a point like somewhere in this interval. I'm going to call that point xi star, because in the ith interval, and then we're going to write the force at that point fxi star. Okay, so that's the force at that point. Now what we can do, since this small is really small, you can assume that the force is a constant in that interval. Okay, so there's a change. But since this small, you can make it really small by dividing into a lot of parts. You can assume that the force is a constant. So that means we can apply the previous formula now, the constant force formula. Okay, so that's what we do. We're gonna bring into that level. So what we can do, let's say work done in moving the object, work done in moving the object from, you can say from xi minus 1 to xi is, so what we can do, so we can use the previous formula. So I'm going to call that work is wi with I position. So it's a force times distance situation. So the force is fxi star. That's a common value, because you can assume that there's a common value for that one. And then the gap is delta x. That's the distance. So again, it's a FD formula. That's the force, this is the distance. Force and the distance. Okay, force and the distance. So now what we're going to do to find the total work done, you're going to add all those intervals. So the total work done is simply, you can say W, which is simply, you're going to add all those small ones. So I going from 1 to n, because there are n many pieces. So you're going to add from each one. Now we can substitute. So if you substitute n, not n, I. So I going from 1 to n, we can substitute. So it's f xi star times delta x. Now what we're going to do is, you're going to divide these into smaller and smaller and smaller part to make the approximation good. Because when you have when you divide into 10, there's a large error. When you divide into 1000, the error goes down. So what we do, we simply send n to infinity to reduce the error to 0. Okay, so we can say considering a large number of subintervals, in other words, send n to infinity, you can say W, which is equals to when the limit n goes to infinity, the sum that you have. So I going from 1 to n, you send n to infinity, f so you have f xi star delta x, and you can see that this is a Riemann sum. So according to Riemann sum, this is simply starting with a, go to b, fx dx. So this simply become fx dx, whatever the f force. Okay, fx dx. So that's the formula for the work. Okay, so you can write. So this is the Riemann sum. So this is a Riemann sum. It's a Riemann sum. So then we can write the final formula as a to b fx dx. So let's start it again. So the so we can say work done by a varying force. Work done by a varying force. Varying force Fx is W equal A to B Fx dx. Okay. So that is the formula for the work done. Good. So this is the formula number 3. Good. So let's do a problem from that. So we can do this problem. So what the problem says, when a particle is placed at x meters distance from the origin, a force 6x squared minus 2x in Newton is acted on it. How much work is needed to move it away from x equal 1 to x equal 2? Always, like, this kind of things are gonna help you, like if you draw it. So the situation is like this. So we can say there's object um, at the origin. So what we're gonna do, we're gonna move it away from x equal 1 to x equal 2. So if you want to move it, so the question is, and then there's a force acting on that object, which is given by that's Fx force, which is a varying force, which is given by 6x squared minus 2x. So the question is how much work you need to move from x equal 1 to 2. So this will be very useful if you are in physics, especially if you try to find work done by a charged particle in the electric field. It's the same problem, because you see there's a varying force acting on it. That's why this is useful in your other courses. So let's try to do it. So the work done is simply work done is simply given by the integral going from 1 to 2 fx dx. So what we can do, we can plug in. So it is 1 to 2, fx is 6x squared minus 2x dx. Now this is a very easy integral. So you can see that if you integrate, you're going to get 2x cubed minus x squared, and then you're going to put 2 and 1. So you're going to get what you get, 2 cube minus 4 minus put 1, you get 2 minus 1, and if you simplify you get 11 joule. By joule, because the force is given in Newton, distance given in meters. Okay, so that's the work done in that situation. Okay, so let's try to discuss something very important. So what we're gonna do is we're gonna talk about the what happens when you have a spring and when you want to stretch it, how much work you need to apply for that. So that's a special example. So spring and Hooke's law. Springs and Hooke's law. Hooke's law. So what the Hooke's law says, so let's say there's a spring which is attached to a wall and placed on a surface. What we can do, we can exert a force. This is what we normally call the natural length. That means if there's no force, that's going to stay in there, and then you're going to start applying a force. So when you apply a force, it's going to stretch. So it's going to stretch. Let's say it is somewhere here. So that's the place. So you put a force. Now it is here. So so it's stretch. Okay. So let's say it's stretch from its natural position. So that's a natural position. Let's say it's going to stretch x distance. That's a x distance. It's going to move x distance from its natural position. Okay. So what the Hooke's law says, when you stretch x distance from its natural position, this x is proportional to the force. So it says that the Hooke's law says, says the force is proportional to the displacement, how much stretched. the distance stretch from its natural position. Okay, there's a natural position, and how much you stretch from that. Um, the force is proportional to distance. So in other words, F is proportional to X. So that's a proportional constant. That's proportional constant is, we normally use K for that. So the Kx. So that is the Hooke's law. F equal Kx, where K is called the spring constant. Okay, so K is called the spring constant. Spring constant. According to the formula, you can find what is the unit of that. It has to be nm minus 1. So the unit of that is nm minus 1. That's the unit. Good. Now let's try to go to the next part. Let's try to find what is the work done by a stretch spring. So let's say work done by a stretched spring. Okay, so you can stretch a spring and how much work it need to do it. Okay, so the same situation that we have above. So you have just a natural position, you're going to pull x distance from it. So what we can do, we know that the force is given by kx. So what we do, we consider this as a varying force and just integrate using the formula that we used before. So the work done is simply W. What we can do is, you can see it's a varying force. So let's try this using a different variable just to avoid the one. So you can see the way the force changing. I'm going to use a t variable so that we can do integral going from ft. Yeah. So yeah, since I use the uppercase F, I'm going to use the same one here. So that means it is ft dt. So you can see dt is the distance that you pull. But you have to integrate from 0 position to x position. That's very important, because 0 is, that means unstretched, and then you pull until x distance. So that means you integrate from 0 to x. So I just use a different variable because I can use x in, out, and in. So that's the otherwise there's nothing different here. So now let's plug it. So you can see this is 0 to x. Ft is given by the Hooke's law, so which is k x, that means kt dt. So that means if we integrate, you can get half k t squared between x and 0, and then you can see if you simplify, you get half k x squared. Very simple. And so that means the formula is, you can say W, which is equal half k x squared is the work done when you stretch a spring. Okay, k is the spring constant. So very simple, very simple. So let's try to do a problem from that just to see how it works. So let's do this problem. Okay, so what the problem says, a force of 40 Newton is required to hold a spring that has been stretched from its natural length. That's very important. You need to find what is the natural length and you stretch from that. So the natural length is 10 centimeters. So if you stretch more than 10, then only it applies a force. Okay. So what the Hooke's law says, the extended length is proportional to the force. That means you always need to subtract 10 in this case. Okay, so from its natural length of 10 centimeters to a length of 15 centimeters, how much work is required in stretching the spring from 15 centimeters to 18 centimeters? So it would helpful if you kind of draw the situation. So what we have, so there's a spring, so which is as at this natural length. That's the situation. And then what we're gonna do, it says that if you apply 40 Newton, it's gonna go to 15. So that's when you apply 40, the force of 40 Newton. That's the natural position. That's the natural position. Um, the natural position. So you apply 40, it's gonna go to 15. So that means this gap is 5. Okay, that's the difference between 10 and 15. And then what's gonna do? They're asking how much work uh, you need extra to stretch it from 15 to 18. So you want to go up to 18. So what is the how much force you need for that? So they are asking the force, but they're asking what is the work you need. So that means there's this natural position. So you go up to 18. So that means it is 8 now. Extended, you extend 8 more. Okay, so this is 10. That's the 10, the natural length. Okay, so that's the kind of situation. Now let's try to use this fact to finish the problem. So okay, so the answer, so the force of the spring is given by the force of the spring. Force of the spring is given by F, which is a function of x equal kx, that we know by the Hooke's law. Now what we need to do is we need to find the k first. So to find k, we can use the first fact. It says that if you apply 40, it's going to extend by 5. Note that F equal 40 Newton when the stretch x, which is 15 minus 10 centimeters, which is equal to 0.05 meters. Okay, we need the standard unit for that. So that means we can use that. So it is F equal kx. So this is 40 equal k, we don't know. X is 0.05. This says that k equal, if you divide 40 by 0.05, you multiply by 100 and divide by 5. So you get 800. 800 nm minus 1. Good, that's the k. So just try to use that information to find k first. Now we know k. So now we can use the formula to find the work done. Very simple. Okay, so the work done in stretching from x, which is 15 minus 10 centimeters to, that means 5 centimeters to x equal 18 minus 10 centimeters, which is 8 centimeters, that means 0.08 meters, is W. So what we're going to integrate from 0.05, that's means 5 centimeters to 8 centimeters in meters. Fx dx, that's the formula says you multiply the f by the dx. But in this case we know that is 0.05. I'm going to write it down here. So it is 0.05 to 0.08 fx means kx, so k is 8x dx. So this is easy to integrate. So it is 400 x squared, integrate from 0.05 to 0.08, and if you plug in that, it is 400 0.08 squared minus 0.05 squared So if you use a calculator, you can see that is 1.56 joule. Why joule? Because we have used Newton and meters. So that's the work done stretching from 15 to 18. Okay, so you remember you always need to subtract the uh, natural length. Okay, so let's go to the next. We're going to do two more examples. The next one is really interesting, what we call hanging chain problems. So let's do that. So that's what we call hanging chain problem. So this is another example of how to use calculus to do a real world problem. So let's say there's a chain uh, like hanging from a corner of a table, something like that. So so there's a table, so there's a chain hanging from that. So that's the chain. So there's a chain hanging from that. Okay. So the question is, if it's a heavy chain, we don't need that long. Okay, if it's a heavy chain, what's going to happen when you want to pull it up to the, so let's say you want to pull this, you want to pull the chain, applying a force. So the thing is that when you want to pull up, what's going to happen, you can see that you are simply lifting, so I'm going to draw it here, you are simply lifting the small part of the chain. So let's say this is a small part. So you can think of the chain is like a small part. What you're going to do is it's like you lifting a book. So when you lift the book, you have the book and you lift that book up. So you multiply the force, that means the weight times how much you lift. But when you have a chain, those are small pieces. So you can think of this the chain is made of small pieces. And then think of you just lift a piece, and then what you're going to do, you add all the pieces. So when you add all the pieces, that's where you need the calculus here. Okay, so you can write a formula for one small part, and then you add all the parts. Add all the part means you integrate. So that's exactly how we're gonna solve the problem. So we're gonna pick a small part. So we can probably say dx, a delta x part. So we're gonna do all the calculation for this small part. Okay, we do all the calculation for the small part, and once you get the formula for a small part, you're gonna add everything, and then that means you simply integrate. So that means if I draw another one, so what's gonna happen, so let's look at this small piece here. So I'm gonna exaggerate, so that is the piece that you're talking about. So let's say this piece is delta x. So what we can do first, we're gonna find the volume or like weight of this piece. There's a weight for that, so we can mark it. So that's the weight of this small piece. So because if the weight of the chain is given, we can find what's the weight of that, and then what we're gonna do is we're gonna apply a force in the opposite direction, and then that one gonna pull it up. So that's the, so this way is gonna go. So and then if you know how much it has to go up, so if you know this distance, how much, so this is height, how far you have to go, then when you multiply that weight of that piece by the height, it's going to give you the work done for that small piece. And then what you can do, you can add all the pieces, or you simply integrate, because you can see that it's going to boils down to a Riemann sum. So let's do like a problem like this. So what the problem says, a 200-pound cable is 100 feet long and hangs vertically from a top of a tall building. Okay, so 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. So these are the questions that we're trying to do. Let's say how much work is required to lift the cable to the top of the building? How much work is required? How much work is required to lift the cable to the top of the building? And also let's do this interesting one. How much work is required to pull, let's say pull up the 20 feet of the cable, only the first 20 feet. Let's say how much work is required, how much work is required, how much work is required uh, to pull up only 20 feet, only 20 feet of the cable. Those are two different problems. In the first problem, they're asking how much work you need to pull the whole cable to the top of the building. Second one, say how much work you need to pull only the first 20 feet for some reason. Okay, so this is like a very typical problem. So make sure that you completely understand this problem, because these kind of problems appear in exams very frequently. Yeah, so let's discuss everything in detail. So now what we can do, so good idea would be to draw the situation. So we can start drawing. So what we have is, so there's a building, um, vertical building, and then what's gonna happen, so there's a cable. So for theoretical purpose, let's say that's the top, and then we have the cable here. So that's the cable. Okay, so the cable. Now what we're gonna do is, so it's gonna so we're gonna measure the distance. So that's another thing, when you get a problem like that, how to measure. So it's up to you how you're gonna do it. So what we can do, I'm gonna measure distance starting from here downward. So if you want to go other way, that's you can. Okay, there's nothing wrong with that. So only thing is you have to think of the new variable. Yeah, so let's not mark this. Okay, so so I'm gonna measure the distance from the top down. So what we can do, we're gonna pick a typical x value. So I'm gonna pick some special place. That's my typical x. So I'm gonna consider the small piece there. Okay. So so that is delta x. So this is the small delta x piece. So what gonna do is, and then you can see the cable is starting from 0, it's 100 feet. So what we're gonna do is we're gonna calculate how much work you need to bring that small piece to the top. So only this part. Okay, that's what we're gonna calculate. Only this part. So the first thing is we need to find the weight of that small piece. For that we have given some information, because we know that the total weight is 200 pound and the length is 100 feet. So then we can find the mass of a unit length, and then we know that the length of this one dx. So when you multiply by dx, you can get the mass of that part, or in this case the weight of that part. So before we do that, let's make the argument. So what we can do, let's try it like that. Divide the cable. So this is like typical argument. Divide the cable into small pieces, into small parts with length delta x. Okay, so we can divide into small pieces which have small delta x length. The weight of such a part is, so we can say F, which is, we know that the 200 is a total weight, which is for 100 feet, but we only have delta x. So this is going to give you the weight of that small piece. So that means you're going to say 2 delta x pound, because delta x also have ft, that's why you can cancel, you get pound. So that is the weight of one small piece, 2 times delta x. So we know the weight. And how much high it need to go? You can see that it has to go x distance up. You can see the small piece has to go this much high. That means that's the distance you're going to pull it. that weight you're going to pull x distance up. So that means if you multiply this F by x, you're going to get the work done. So the work needed to lift delta x bar to the top. Let's write the work needed um, to lift delta x part to the top of the building is simply F times no, we write the work W equal F times D. In this case, F is 2 times delta x, that's the weight, times how much? You need to pull x distance up. So that is the weight, that is the distance. You can multiply these two. So that means you can write this one as 2x delta x. So that is the work done to lift that small piece. Now what you can do? You can add all the pieces. That means you simply integrate this one. Okay, so the work done pulling the entire cable to the top is the work done in pulling the entire cable to the top of the building is W equal, you can see, okay, so what are the distance? You can see you need to add all the pieces. That means you need to add from 0 to 100 everything between 0 and 100. So it is from 0 to 100 fx dx. So that means in this case it is simply 0 to 100. It is 2x dx. Delta x become dx when you write as an integral. This is a very simple integral. This is x squared 100 to 0, and then you can see that this is 10,000 feet pound. Okay, so that's the amount of work that you need to pull the entire cable to the top of the building. It's a very simple integral. But if you understand what we did, so again what we did, we try to find the weight of the small piece. Okay, that's what we did here, weight of the small piece. Once you get the weight of the small piece, you multiply by the distance, how how much it need to go up. You can see, since the x distance, you have to go x distance up, then it's that small piece on the top. We makes a lot of assumptions there, because you can just leave it on the top, it's gonna fall down, but we don't worry about that. Okay, and then so that means that's the amount of work you need to pull the small part. Now what we do it, after you find for a small part, you're just gonna integrate to find everything. Okay, that's how we do. So you can see you simply integrate 2x. Okay, good. And then if the mass is given, so you have to be careful. If the mass is given, you first need to multiply by the g to find the weight, and then the rest of the calculation would be very similar. Okay, so if the mass is given, you need to calculate the weight first by multiply by g, and after you do that, then use the standard units. You just multiply by the rest of the calculation would be similar, but you need to multiply by g. But when you have the pound, weight is given in pound, you don't want to do that. Okay, that's the major difference between the two. So let's start with the second part. So what the second part says, you only pull the top 20. So top 20 would be exactly the same as the previous one. so we can do that part first. So the work done, okay, uh, work done Now let's try it like that. Let's say work needed to lift the uh, top 20 feet, only the top 20 feet, top 20 feet of the cable is very similar. I'm going to call that W1. So what do? You only need to from 0 to 20. That's the only thing you need to add. 2xd is exactly the same as before. So that means x squared 20 to 0. So you get 400 feet pound. Okay, but the thing is that when you pull only the top 20 part of the cable, you can see the bottom part also pulls up. But how much? The whole cable, the rest of the whole cable pulls up 20 feet. Each piece go only 20 feet up. So that means that calculation is different from the previous calculation, because in the previous calculation different part move in a different distance, okay, depending on how, where it lies. But the rest of the piece, you can see that every piece go 20 feet. So that means in that case it go equal distance 20. So that means the calculation is slightly different from the previous one. It's a little easier. So I'm going to write that first. So when doing so, okay, when you pull only the first 20 part, that's why when doing so, at the lower 20, you are 80 feet lower, the lower 80 feet part also lift by 20 feet. Everything only 20, exact same number. So the work done is, you can see this calculation is slightly different. I'm going to call it W2 is what? You can see, I'm going to talk about the limit later. So you can see each small part has 2dx weight times how much is going to pull up. It's going to pull up 20. So that's the distance. So this is the D. It's 20. Here, this is the force. So you can see it's a slightly different calculation, because force is 2dx still, but each piece go 20 feet up. Now you need to calculate all the pieces starting from 20 to 100. You need to calculate. You have to do this calculation for everything in between 20 and 100. Good. So now, so it is 20 to 100. You can see 40 dx. So you can pull the dx out. So it is simply 40x 120. So this is a very simple calculation. So you can see the 40 times 100 minus 20. So it is 3200 feet pound. Okay, so that's for the second part. Now the total work done is the sum of the two. So the total work done is W1 plus W2. So you can consider this as two different pieces, because in the first piece you can see that the distance traveled is different from piece to piece, but for the second part, the whole part go 20 feet up. So it's the same for it. That's why we did it in a different way. So it is 400 for the first part, 3200 for the second part, so it's 3600 in total for the whole cable. So this is the calculation we did. So you see that you have to break that problem into two different parts and do it. Okay, so let's do the last problem. So last problem is kind of very interesting, what we call a conical tank. So we can do a tank problem. So what happened, I mean, you can do different type of problems, but we're gonna do, I'm gonna show you how the geometry works here. So we're gonna look at a conical tank and put some liquid in there and then try to empty it. So how much work you need to do that? Okay, that's the kind of problem we try to do here. So what we call conical tank. So it can be any type of problem, but we do that one here. Okay, so this is a special problem. I'm going to put a star here because these kind of problems are very common in exams. So so this is the problem. So so what it says, an inverted conical tank of radius 4 meters and height 10 meters is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all the water to the top of the tank. So again, what it says, an inverted conical tank. Inverted, that means upside down. So like a like that. So it's inverted like this way. That's inverted conical tank. So you have a conical tank, but it's upside down. An inverted conical tank of radius 4 meters and height 10. So the radius is 4, and the height is 10. Okay, so it says height is 10. Is filled with water to the height of 8 meters. It's not all the way, but only about 8 feet. Okay, only about 8. So this is 10. You put only 8. So they're asking, what they're trying to do is you try to empty it. So you try to empty all the water. By pulling the water, you pump the water to the top of the rim, to the rim, and then asking how much work you need to do it to do that. How much work you have to do it. So let's start first drawing in detail. You know what we have, because that's definitely going to help you. Okay, so let's draw it. So this is the cone. So you can see that. So this is that's a radius. So this is 4 meters. And then we have the height. So height is 10 meters. So height is 10 meters. And it says that the water is filled only up to 8 meters. So that's the water level. It's only up to 8. Okay. So now what we're gonna do is yeah, that's the water level. So I'm gonna mark it only 8 meters. So there's a 2 meters from there. That's 2. Now what we need to do is what we're gonna calculate the work needed for a thin small slab. So so let's mark that. So I'm gonna consider a small slab here. So that's a really tiny slab. So that's a slab. So what we're gonna do, we're gonna calculate the work needed to pull this slab to the top. That's how we're trying to do. We're gonna pick a small slab and we calculate the work needed for that slab. So let's try to calculate. So we need to calculate a few things. For example, we need to calculate what is the weight of this slab, and then we can calculate how much work needed to bring this slab out of the because you can think of this one as a tiny cylinder. Okay, so that's how we're gonna do. So assume few things. So I'm gonna call the radius. I'm gonna call the radius of this one is r. So let's call this one has a radius r. And then now the thing is that I have seen like similar problems in several books. In some books they do this in like a really complicated way. I'm gonna do it in a slightly like easier way. So if you see a similar problem, compare my method with the other method that you have seen. So what we're gonna do, I'm gonna measure the distance. So that's the major difference from the bottom. Okay, so let's measure the distance from the bottom. So I'm gonna measure the distance from the bottom. So let's say your slab is at the x distance. So this is x. Okay, from the bottom, from the top. And then now, how much high you need to bring this slab to the top? You can see the top, the total height is 10. That means only 10 minus x is left. So this is how much you need to bring this slab up. Okay, so if you know the weight of the slab, what you need to do is simply multiply by 10 minus x, because that's how much you need to pull it up. So this is very similar to the cable problem, okay, or the book problem, any problem, because you know, if you know the weight of that small slab of water, then what you need to do is you need to see, you just multiply by 10 minus x, because that's how much you're going to bring it to the top. So you only need to find the weight of that simple this simple slab of water, this tiny piece of cylinder. Okay, so we have everything we need. So we need like a little bit of geometry here, because we don't know what the radius now. So what I'm gonna draw this triangle. So we have a triangle like this here. So we have 10, and then we have 4 this way, and then I'm gonna draw this similar triangle. And this is the slab that we mark, just this part. You can see this is a 90-degree. So this is the radius r of the slab. This is the 4 of the big conical the cone, and this is the x distance, and you can see this is 10, so this is 10, that's the total height. So now we can use the similar triangles here. So if you by similar triangles, by similar triangles by similar triangles, we have we can see that r divided by x is exactly similar to r divided by x is exactly similar to 4 divided by 10, because you can see those are the corresponding pieces of those two triangles. There are two triangles. One triangle is here, and the other triangle is this big one, this big triangle. So and then we're going to write the corresponding sides. So you can see r corresponds to 4, x corresponds to 10, and from this one you can find r. So what is r? If you multiply by x, and you can simplify this one, because this simplifies to 2/5. So that means r is simply 2/5 x. Okay. So that's a big piece of information that we need. We get r as a function of x. Now we know the radius. Since you know the radius, then we can find the volume of that. And once you multiply the volume with the density, you're gonna get the mass. Okay, once you know the mass, multiply by g, you're gonna find the weight. So let's do all of them now. Okay, so next, so we have the r, so that's the big one we need. So we get that piece. Now we can do the rest, because that's what we are looking for, the radius of this small slab. So the rest goes as follows. So we can say the volume, the volume, the volume of uh, the volume of the slab, slab, uh, slab, the volume of the slab uh, of water. Okay, that means small thin disc is simply, I'm going to call it the VI, the eyepiece if you want. So it is pi r squared h, because it is a cylinder, so it looks like a cylinder. So that's why we use as r, and that is the h. So the volume is given by pi r squared h. Okay, that's the base area times height. Base area is pi r squared times height. Good. So we have that. So let's plug in. So that means it is pi. R is, we calculate that is 2/5 x squared h, because this is a small tiny piece, the height of that small tiny piece is delta x. That's what you're looking for, small piece. Okay, so if you simplify this a little bit, you can say that this is 4 pi over 25th x squared dx. So that is the volume. Now since you know the volume, then we can find the mass by multiplying by the density, because we know this formula. So I'm going to recall one of the other formula. So we know that the density equal mass over volume. So that means if you need the mass, which is the density times the volume, so we can use that formula to find the mass of that. Okay, so if you know the mass, to find the weight, what we're going to do is simply multiply by g. Okay, so the weight of the slab, weight of the slab is simply F, you can say I, the eyepiece, it is M times G, mass times G. mass T is simply density times volume. So we can write this is the density times the volume. Volume we calculate just above times g. G is the gravitational acceleration. So let's multiply by that. So we know the density is 1000, that's given for water, and the mass volume we just found, it is 4 pi over 25th x squared dx times g. G is a gravitational acceleration that we know that 9.8. So if you use a calculator, you will end up with 1568 pi x squared dx. Dx is delta x. Yeah, so you can write the delta x for dx. I switch. Yeah, if you don't like it, you can change that to delta x. So it doesn't matter. So yeah, let's change everything to delta x. Okay, so delta x. That's a small slab. So delta x and delta x. Okay, good. So when you integrate, delta x become dx. Okay. So when you integrate, you're gonna switch delta x to dx. Good. Okay, now so that's the weight. That's the weight of the slab. Now what you need to do is what we need to do, we need to calculate how much work you need to do to pull this slab to the top. So you can see that how much you need to pull. You need to pull only 10 minus x distance. That's how much you need to pull. Okay, so let's try that. So the work done, let's say work needed, uh, uh, work needed to pull the slab to the top is simply Wi, which is the F times the distance. F we already know, so that's Fi times the distance. How much? It is 10 minus x. That's how much you need to pull up. Now let's plug in here. So if you plug in here, you're gonna get 1568 pi x squared 10 minus x dx, delta x. Okay, so now what we're gonna do is you simply, so that is just for a small piece. Now what we can do, we can integrate this. Okay, so the total work done is simply the integral of, because this is for the small piece. Now what we can do, we're gonna add all the pieces. Adding all the pieces means you integrate. So let's do that. So the total work done is you integrate that. Integral means delta x become dx. So it is w, which is simply 1568 pi x squared 10 minus x dx. Delta x become dx. What's the limit? You can see that you have to do for everything between 0 and 8. That's where the water is. So from 0 to 8. So let's do that. And you can see, to do that, you can distribute this part to get a function of one function, but there's no product rule. And then you can also pull out 1568, you can pull it out pi. So we have 0 to 8. And then when you distribute, you're going to get 10 x squared minus x cubed dx. This is a very simple integral. So 1568 pi, integral is 10 over 3 x cubed minus x to the 4th over 4, and the numbers are 8 and 0. So if you plug in the values, you get 1568 pi, and if you simplify this part, you get 2048 over 3. And if you say, so that's the exact value. So this is joule in Newton meters, and if it's a calculator, you will get something like 3362827.79 joule. So if in kilojoule, that means you divide by 10. So 3362.8 kilojoule. So that's the amount of work you need to do. So that's the integral, but you need to understand how you derive the formula. Okay, because these kind of problems are very common in exams. Thank you. So this is the end of the work lecture. Thank you.